Hello, GH101. In this video, we're going to review a bit and do a bit new by shamelessly stealing and using Harvard's version of CS principles. I put a link here up at the top. Up at the top here for this version of CS50. So if we go there, we're going to be looking right now in the computers and computing. And inside of each of the chapters, there are modules. They will often have videos and slides. Okay, so I'm just sort of going to go through here and keep track of supplementing our notes potentially, and also terms for the next quiz. Okay, so in the computers and computing, what is a computer? And what they come up with eventually is a definition. A device that accepts data or input and processes it in some way to automatically produce a result. And all of these individual words are important. So a computer is a device, not a person. There has to be some kind of input coming into the device. Right now, my computer is taking input from my voice on the microphone and also from the mouse. Okay, the computer does something. Processes is just a word for does. And automatically, so the computer works on its own. It uses its own code. The person does not have to turn a crank wheel to make the computer work. And it has to produce some kind of result. So it does, there is something that's supposed to be achieved in the end. Right now my computer is listening to my voice and recording a video. So the video is going to be the result. Alright, now I have put that under our notes, definitions to memorize. So that's just a definition that I'm allowed to ask you to repeat it word for word. It's a cute, there's lots of different definitions of what a computer is. That's one that we'll use. Alright, what is computing? There are various definitions of computing that they take from the web or somewhere. I'm just going to look at a few things here. So here they have a bunch of numbers. 1, 2, 3, 4, 5. I'm not sure what they're doing here. Let's skip to, I wanted to use some of their, so these are some things that are part of computing that computing does for us. This is a picture of a GPS map. And so doing all the map stuff, how do we figure out how to make the car, how do we figure out the fastest way to get from where the car is to where we want to go? If I want to go from Terre Haute to San Francisco, what's the best route? There are computer algorithms to do this. Algorithm will be something that we'll have in our list as well of just definitions that have to be memorized. For now, we'll take as our working definition a precise way to solve a problem. What are the exact steps? Okay, so how do we exactly have the computer figure this out? There's chess, and there are many things you could say about chess related to computing. One is the question, can you come up with a way for a computer to choose moves in a chess game so that it will do well and win? There are algorithms for this. There are algorithms that tell, based on what the chessboard looks like, where are all the pieces, what should the next move be? Okay. How computers work. So now there are some videos if you want some more about any of this, how computers work, CPUs and graphics cards and things like that, you can check out there. I just want to review their slides. This is a motherboard, and you could pause right here and see all the different things that plug into the motherboard. The motherboard is where everything plugs into. And this is an older motherboard. Maybe it's, this is probably 15 years old, just based on the ports here that are, this is where you would hook your keyboard in. Keyboards don't have that kind of connector anymore. Now they're USB. And these are USB right here. Okay. They're talking about the different parts of a computer, which we've talked about. And that's it. See how fast we're getting through what they were doing. I want to skip over, let's skip over to things we've already really done. Hardware. And actually, we've already done all this as well. So we can skip this as well. Excellent, we're moving fast. And okay, so we'll start to get into some things that are new and take notes as we go. All right, so Bits and Bytes, and you can see that their version of this is, it looks like an hour. Let's see how long it takes us to get through, just with the most important stuff. If you want to pause for a second, you could pause. All right. So we have our definition of a bit. We've already done that. It's 0 or 1, on or off, true or false, yes or no. A byte is 8 bits. A kilobyte is 1,000 bytes, and that's just the kilo from the metric system. Okay, a megabyte is 1,000 kilobytes. So here they're going doing this 2 to the power of 10 business. So let's go ahead and take some notes somewhere. And we'll put this under the category of binary. Okay, so what is the value of 2 to the 10th power? What does that mean? So what that means is you multiply 2 by itself with 10 copies. Okay, and then if you do all that, what do you get? Plug it into your calculator, you get 1,024. Let's put this back up under units. We'll get to binary. So far we don't have to talk about binary right there yet. Okay, so in computer usage, kilobyte could mean 1,000 bytes or 1,024 bytes. The reason that we may prefer to talk about 1,024 bytes is on a computer chip, it may be more likely to actually have this show up as the number of bytes as opposed to this, just because of things being done in powers of 2. Powers of 2 just come up all over the place in computing. Okay, so if we look up kilobyte and see what Google says, they say, so here's the 1,000 and here's a 1,024. So so they actually have a different abbreviation for the power of 2 version of metric prefixes. So instead of 1,000, we use 1,024, and that's capital K-I-B, kibibyte. You can look up the etymology for that. So if you say KB, it probably means 1,000 bytes. If you want to mean 1,024, it would be kibibytes. And there's the version for all of those. A megabyte is 1,000 kilobytes. A mebibyte is 1,024 kibibytes. And this is something that you should just remember, that 2 to the 10th is 1,024, which is close to 1,000. And 2 to the 20th power is 1,024 times 1,024. It's 20 copies of multiplying 2's together, so I have 10 copies of multiplying 2's together times 10 copies of multiplying by 2's together, and this is close to 1 million. All right, what about 2 to the 30th power? What is that going to be close to? Pause for a second. And what's the answer? Well, it's 1,024 times 1,024 times 1,024. That's close to 1 billion. About 2 to the 40th power. What is it close to? It's another roughly 1,000 multiplied on. So that's close to 1 trillion. Okay, so if I talk about 1 billion bytes, gigabytes, that also happens to be 2 to the 30th power. Okay? Fun. And I think they're saying here something that is measured in kilobytes would be a Word document. If you go take one of your Word documents and look in File Explorer, how big is it? It'll be in kilobytes, most likely maybe 100 kilobytes. Something that is roughly a megabyte is music. So a song, a MP3 song is maybe 3 megabytes. Okay, then we get up to gigabytes, which we've already discussed. And something that's of size of gigabytes is a USB flash drive. That's probably 8 or 16 or 128 gigabytes. Terabyte is the next multiple of 1,000. And currently, disk drives and solid-state drives are around a terabyte, 2, 3, 4 terabytes. Okay, did we include? Yes, those. All right. So that's bits and bytes, and they took an hour, and we took 7 minutes. If you want to pause here, let's see. You can pause here just to soak in the powers of 2 business. And moving on, we'll go to the next module, which is, okay, we already looked at hardware. Let's see what they say about memory. I believe there's only one thing that I wanted to emphasize. Okay, so they end up having a drawing that looks like this, different types of storage. So we have a hard disk drive, which is large, like terabytes. We have memory, which is abbreviated RAM for random access memory, which is in gigabytes. And then there's memory on the CPU, and these are different levels of memory on the CPU, L3 cache, L2 cache, L1 cache, that are faster than RAM, but also more expensive. And then we have the CPU itself. And I'm actually going to take something from the operating systems course I'm also doing right now. Let's see, it was down here. This. Okay, so this is a table from an i7, a Core i7 This is maybe a vintage 2017 CPU. And here we have the time it takes to access, so how fast is it? And here we have how much of it is there. Okay, and we can take some notes on this in an appropriate place. So we'll do storage. So long-term persistent, we have that is HDD or SSD. Short-term volatile, we already had memory for that, but now we're going to add on CPU cache and CPU registers. Access times as of roughly 2017 to 2018. We're going to go with, so register, L1 cache, L2 cache, L3 cache, and random access memory. Size, vintage 2017 to 2018. Register, L1 cache, L2 cache, L3 cache, and memory. All right, memory we already know this is in gigabytes. So they don't have that in here, but all right. And then on the other side, a CPU, the actual, when it's actually adding numbers or dealing with numbers directly, that's on the CPU chip itself. It's in something called a register. And according to this, okay, register, there's maybe 64 bytes of that on this particular chip. So this is 64 bytes. All right, and then we have the L1 cache is 64 kilobytes. So we went up from bytes to kilobytes. And then we go L2 and L3 are in megabytes. And this is 4 megabytes and 8 megabytes. Okay, so this L1 cache and register is much smaller. You can't hold too much there, especially the registers. There's really not much you can only put in there what you're currently working on, really. All right, but then if we look at the times, a register takes 1 cycle. So if we have a 2.4 gigahertz chip, then we can read that register in 1 over 2.4 billion, 1 over, let's see, 1 over 2.4 billion. So a 2.4 billionth of a second is how long it takes for a register. The L1 cache is 4 times slower. The L2 cache is another 2.5 times slower than the L1 cache. And then we have L3, which is, say, 5 times slower than L2. And then you get to memory, which is slower still. All right, so let's put this as 1 cycle. And we'll put this as, instead of saying 4 cycles, it's 4x slower than register. And this was 2.5x slower than L1. And the L3 we said was about 5 times slower than L2. Put that over here. And then to put the memory, we need to do some calculations. Let me pause for a second. All right, let's go over and figure out this nanoseconds versus 1 CPU cycle. So maybe we'll take notes right. Note we had 1 cycle is 1 over 2.4 billion on that on that CPU, and we're going to put here 100 nanoseconds. Okay, so how many cycles is this 100 nanoseconds? First, we need to know what is the abbreviation for nano, and in our metric prefixes, nano's down here, 10 to the minus ninth, 1 over a billion. Okay, 100 nanoseconds is then 100 times 10 to the minus ninth. So we could say 10 squared times 10 to the minus ninth, which is 10 to the minus seventh, or 1 over 10 million. Okay, so how many cycles is this? When a cycle is 2.4 billion. So I want to know, say, some number, say h, just some h. So I want to know what times 1 over 2.4 billion, right? This is the time it takes for one cycle, and I want to know how many of those is going to equal 10 to the minus seventh. Let's write this as 2.4 times 10 to the ninth. Okay, so we have h over 2.4 times 10 to the ninth equals 10 to the seventh. Okay, so that means if we just multiply through, we've got h is 10 to the ninth. We need to multiply by 10 to the ninth to get it out of the denominator over here. If you don't like this, then write it down on paper. For now, all right. This is like this now. Okay, so h divided by 2.4 times 10 to the ninth. So we have to multiply by the 2.4 to get it out of this denominator, so that's going to be on that side. And we have to multiply by 100. Or sorry, multiply by 10 to the ninth. That cancels out this and is left with 10 to the second power. So that's 2.4 times 100, 240. So this is 240 cycles. Here we had 100 cycles, so that's another 2.5x slower. All right, so as we go from faster to slower, we get larger sizes and they get less expensive as well. So having a CPU with more, twice as much cache, that may be just as much as doubling the amount of memory. So it could be that getting 16 megabytes of cache instead of 8 would be just as much as going from 8 gigabytes of memory to 16. All right, so we're going to leave it there as part 1. I think that's part 1, and then we'll do the next video. This is some new content, so we'll review their slides, and yeah, that's the end for now.